Picture a future where information moves at the speed of light, and not just in theory, but in practice. As our need for faster data and smarter system grows, we're turning to a powerful new solution, silicon photonics. Hello, I am Micaela Narin and Quarteron from Bachelor of Science in Computer Engineering Department, and today I will be discussing with you the invention silicon photonics. I will be tackling its definition, its operating principles, the history of its chemical composition, and many more. So let's start with the question, what is silicon photonics? So silicon photonics is a technology platform that uses silicon to create photonic integrated circuits, or PICs in short. It is also the study and application of photonic systems that use silicon as an optical medium. So these circuits manipulate photons or light instead of electrons, which is electricity, to transmit information. So by utilizing silicon on insulator or SOI wafers and standard CMOS manufacturing process, silicon photonics enables the production of photonic circuits at scale and at a lower cost. So basically, in simple terms, it is about using light instead of electricity to transmit information on chips, especially for high-speed data communication. While traditional electronics transmit signals using electrons, silicon photonics relies on photons, which are the basic units of light, yet it still takes advantage of the same fabrication methods used for silicon chips. This makes it possible to produce photonic circuits efficiently, affordably, and on a large scale. So now I will discuss what are the advantages of silicon photonics. Okay, so first we have high bandwidth. This is the where light can carry more data than electricity or electrical rather signals. And then there's also energy efficiency. PICs consume less power and also generates less heat. There's also lastly is scalability, which means that it is compatible with the current existing semiconductor fabrication techniques, which allows integration with electronic components on a single chip. So now next, I will be discussing the applications of silicon photonics. So there's data centers, telecommunications, healthcare, consumer consumer electronics. So for data centers, it is the enhancing of data transmission speeds, and for telecommunications, it's about improving network performance. And then there's healthcare, which is the enabling of advanced imaging and also diagnostics. And lastly, the consumer electronics, which is the supporting of high speed data transfer in different devices. Okay, so now we have the main topic, which is the chemical history of silicon photonics. So when we talk about silicon photonics, we often focus on speed and, as I've said before, bandwidth and also the innovation itself. But behind this great technology lies a story that is rooted deeply into chemistry, which is the chemical evolution of silicon and how it became the backbone of modern photonics. So silicon is the second most abundant element in the Earth's crust and has been known since the early 19th century, and it was first isolated in pure form by the Swedish chemist um here Hans I think it was pronounced as Jons Jacob Berzelius in 1824 through the chemical reduction of silicon tetrafluoride with potassium. This breakthrough marked the beginning of silicon's journey from a lab curiosity to the core material in microelectronics and photonics. So, in the 1980s and also 90s, researchers began to explore um, how silicon could manipulate light, not just electrons. Despite silicon's indirect band gap, chemists and material scientists rather found ways to guide, modulate, and then also detect light in silicon-based structures. And then by the mid 20th century, silicon's semiconductor properties were harnessed for transistors and integrated circuits. So chemists refined methods to produce ultra pure silicon using the Choralsky process, wherein silicon is melted and also recrystallized, which it turns into monocrystalline ingots. So this high purity silicon with controlled doping using elements like boron or phosphorus, it laid the chemical groundwork for electronic chips and then eventually the photonic ones. This led the development of silicon on insulator or SOI wafers created by chemically bonding layers of silicon and silicon dioxide. So this structure became the foundation of silicon photonic circuits. And then to overcome the light emission limitation of silicons, researchers have chemically integrated it with other materials like germanium for detectors, and then also 3,5 semiconductors for lasers. So these hybrid approaches require complex chemical bonding and deposition strategies to align different crystal structures, which is a remarkable achievement in the materials chemistry. From elemental silicon to advanced photonic circuits, chemistry has played a central role in shaping the field of silicon photonics. As new materials and processes emerge, the chemical evolution of this technology, silicon photonics, will continue to push the limit of what's possible. So now we- we're discussing silicon photonics in relation to computer engineering. So how does this relate to computer engineering? So computer engineering combines hardware design, electronics, system architectures, and many more. And silicon photonics directly impacts all of these areas. So let's discuss how it is like in hardware architecture. Silicon photonics enables optical interconnects, so replacing copper wires with optical links inside and between chips. This also allows CPUs, GPUs, memory units to communicate faster with less latency, which is next is system performance. So as data moves faster, processors can work more efficiently. This is especially critical in high performance computing, data centers, and also AI accelerators. So, lastly, there's thermal management. As I've said before, light generates far less heat than electricity. So, engineers will be able to build systems that are cooler and more power efficient, which is essential in tightly packed server farms. So, in conclusion, silicon photonics is more than just a technological innovation. It is a powerful convergence of physics. There's also engineering, chemistry. By harnessing the speed of light and combining it with scalability of silicon, this technology addresses the growing demands for faster, more efficient, and also a more reliable data transmission. So now, to gather up, we've explored its definition, the way it works, the chemical evolution that made it possible, and also its role in computer engineering, from improving system architecture to enhancing performance and also thermal efficiency rather. And then as we continue to push the boundaries or limitations of computing and connectivity, Silicon photonics will undoubtedly play a central role rather, in shaping the future of technology. Thank you for listening, and I hope this presentation has helped you better understand the remarkable impact and potential of silicon photonics.